So our next speaker coming up, by the way, it's 25 to 27 degrees in the Breckenridge area. It changes rapidly. It's now 26, Dale says, interpolating between the 25 and 27. Our next speaker here is an incredible speaker and talks a lot about an incredible topic that I think not many people spend quality time learning about. We often talk, or those in the room often talk on the air about drought conditions, how much below or above average it is, whether it's an extreme drought, whether it's a developing extreme drought. But what tends to get left off are the implications of that drought. And I know I've seen stories around to talk about agricultural impacts and things like that. However, I really think it's important for everyone to understand the root causes of certain issues. Many times point to drought. And we are seeing an extreme one in California. So our next speaker is Dr. Peter Gleick. He's the co-founder of the Pacific Institute. And so we're going to take a look and dive a little bit deeper into the implications of water and drought and how that plays into security issues as well. So as an introductory video, take a look at Peter Gleick, and we'll get right into his presentation.
We're pleased now to be joined by Dr. Peter Gleick, president and co-founder of the Pacific Institute in Oakland, California, and the co-editor of A 21st Century U.S. Water Policy. Dr. Gleick, many thanks for your time this evening.
Happy to be here.
Well, thank you. So let me start off with the scary question. How major of a water crisis are we facing now in the United States?
I think we're facing an increasing water crisis. I think we're seeing competition for water resources in places we didn't used to see competition for water. I think we're seeing more and more contamination of our water resources. The reality is water in the United States is limited, and increasingly we're seeing conflict, we're seeing tension, we're seeing disputes over who gets it, who uses it, what they do with it, and I think we're in a situation where those conflicts are going to get worse, not better. I do think one of the biggest challenges is managing the water, and do we manage it as a public resource? Do we manage it as a private good? There's a lot of contention over that, and in the United States it's been a public good for a long time. We have excellent public agencies that manage our water resources, but we have to get better at managing it, and we have to realize that water is both a human right, but it's also an economic good, and we have to balance those challenges. The additional problem is that climate change is going to affect all of these issues. Climate change is going to affect how much water we get, where we get it, the severity of extreme events. It's going to put more pressure on proper management of this limited resource.
Well, you answered my next question, so let me just finish out with what impact do our domestic water disputes have on the rest of the world?
Well, in the United States, we're actually a little more fortunate in that when we have disputes over water, we take it to court, we negotiate, we have conversations, hopefully, about those disputes. But there's a long history of violent conflict over water internationally, going back 5,000 years. We fight over access to water. Water is a target during wars that start for other reasons. We use water as a weapon. One of the things that we do at the Pacific Institute is maintain a history of conflicts over water going back for millennia. And it looks like conflicts over water are growing as climate change affects water availability, as populations grow, as the demand for water grows. Water that crosses a border, a state border, an international border, we're beginning to see more and more violence, injuries, deaths, disputes over those shared water resources. And we're not good at managing water now, and if we don't get better, the risks of conflicts are going to grow, and the challenges associated with conflicts are going to grow. Well, good morning, everyone. Good morning to all of you in the room. Good morning to everybody who's online, the thousands and thousands of people who are watching online. I appreciate the invitation to participate in the Weather and Climate Summit this year. It's been a very exciting week for me. The talks have been fantastic. The conversations that I've had have been really interesting and enlightening and informative to me. I'm a water guy. I'm a climate guy. My background is hydrology and climatology. It's been interesting to see that I tend to think about climate in terms of what's going to happen over decades and centuries. This audience thinks about weather in terms of what's happening in the next couple of hours, or over the next few days, or maybe over the next week or so. There's a difference there, but there's a similarity there. And part of what I'm going to talk about today is, in a sense, the way that weather and climate are coming together, both in the work that we do and in the issues that we face. And I'm going to talk about that increasing interaction. The other thing I wanted to do before I actually get into my talk, though, is provide a little bit of perspective that I've gotten. Again, I'm a climate guy. I've learned this week that you cannot have a normal weather conversation at breakfast with this particular group. And many of you may have seen this. This is a cartoon by Randall Munroe from XKCD. I'll let you read it. This is the kind of conversations I've been having at breakfast. And it says at the bottom, of course, weather geeks have it tough. I suspect this is the kind of conversation you have with your family and your spouses and your friends. They ask you, well, how's the weather? And this is the kind of response that they get, and they're sorry they asked. Another piece of perspective, though, again, before my talk, is we often think about the world like this, a big globe, and we see our weather satellites looking down and our environmental satellites looking down, and they give us information about this massive thing that is the Earth. But the reality is that the weather occurs and the climate occurs in an incredibly thin film over the planet. We're in Breckenridge, Colorado. You go 20 miles north or south or east or west of here, and the truth is you're still pretty much in the same valley. You haven't really gone anywhere. You go 20 miles up, and you're out of the atmosphere, really, out of the effective part of the atmosphere where all of the weather occurs. The weather occurs in an incredibly delicate film around the surface of the planet, and I don't think people really fully understand that from a perspective point of view. And I think it's an important point to our understanding basically about how delicate the atmosphere really is, and ultimately how humans are able ultimately to affect the weather and, in the long run, the climate. So I'm going to talk about a bunch of different things this morning. I'm going to talk about climate and extreme hydrologic events. What do we observe? What do we expect? What do we see? I'm going to talk about why we care. And I'm going to talk about it in the context of a number of things. I'm going to talk about the California drought from 2012 until we're not sure. I'm going to talk about food and agriculture and the impacts of the drought. I'm going to talk about water and conflicts. We do a lot of work, as that introduction suggested, at the Pacific Institute on conflicts over water internationally. And I'm going to talk about it in general, and I'm going to talk about it specifically in the case of Syria. Which I think is an interesting example of the connections between drought and weather and water management and politics and ultimately violent conflict. And then I'm going to talk a little bit about, at the end, about what maybe we ought to do about some of these issues from a policy perspective. So let me start with climate and the extreme hydrologic events. I'm going to talk about what do we expect in the context of projections. I'm going to talk about what we see in the context of observations. I'm going to talk about the risks of extreme events in terms of the vulnerabilities of our society and our ecosystems to these kinds of extreme events, and then a little bit about how we respond and what we ought to do about it. So let me start with projections. Projections, of course, come from our basic physical understanding of science, our understanding of atmospheric dynamics, the basic behavior of atmospheric physics, but it also comes from models that we produce to try and represent and permit us to forecast what might happen from a weather perspective on a day-to-day basis or from a climate perspective from decades to centuries out. In terms of climate impacts on water resources, some of the things that we expect from our understanding of the atmosphere are increased atmospheric temperatures, less snowpack in mountainous areas, and more rain as temperatures go up. More precipitation as rain than snow. Changes in timing and the amount of runoff in our rivers, which is important for water managers. Changes in the way we operate the system based on these projections. Sea level rise, and there have been interesting talks here about sea level rise. Changes in the Arctic. There are all sorts of things that are understanding of physics and our models tell us to expect. And I'll give you some specific examples for the United States. This is a map of projected seasonal precipitation changes over the course, these are climate projections, over the course basically of the coming century for the last decade in the 21st century, 2080 to 2099, from the US Global Change Research Program, based on one particular climate model. And there are a number of things to understand here. First of all, we see the different seasons. In blue, we see expected increases in precipitation. In the brownish colors, we see expected decreases in precipitation. And the darker the color, the greater the expected change. One of the things that is important to observe here is that there's a boundary between where we expect precipitation to increase and where we expect it to decrease. And I would say most models, climate models, show this same kind of transition from increases in precipitation in the higher latitudes toward the Arctic and decreases in precipitation toward the mid-latitudes and toward the equator, just based on the way the atmosphere delivers water around the planet. But in this middle zone, where precipitation may increase, are the greatest uncertainties. It's where the models are least likely to agree. And unfortunately for the United States, that happens to be right smack in the middle of the United States. And so I live in California. One of the things we would really like to know from a water perspective is, over time, as the climate changes, is precipitation going to increase or decrease? And we have the greatest uncertainties in this region of the United States. Increasingly, as the models get better, we're getting better consistency among these projections. And we've heard talks about ensemble and probabilistic forecasts. There is a growing consensus that, for example, the southwestern United States will be dry. And you see it here. This is winter precipitation, spring precipitation, and so on. But this part of the United States is pretty consistently dry in these model forecasts as we go out in the future decades. And of course, from a water perspective, that's the opposite of what we would like. We would like it globally if wet areas got maybe a little drier, if dry areas got a little wetter, reducing the risk of floods and droughts, but unfortunately that's not what the models are projecting. If we look at projected changes in runoff, which is the result of a combination of precipitation and temperature, this is what we see. And the scale is toward the red. These are percent changes in precipitation in these regions. Red is really significant decreases in precipitation. Blue is increases in precipitation. And again, this shows, for example, for the southwestern United States and for the western United States, big drops in runoff over time. The cross-hatching are areas where our models have a greater confidence level. And again, for the Colorado Basin, this is not what you want to see. You don't want to see decreases in precipitation in the Colorado Basin or in the western United States. These are areas that are already arid, they're already water scarce, we already have water challenges, and that's going to be a problem. Okay, so another piece of this puzzle is snowmelt, and the last talk was focused on the importance of snowfall and snow dynamics, and certainly for water resources and for mountainous water resources, snow is an incredibly important issue. If you're interested in skiing, snow is an incredibly important issue. And with a very high degree of confidence, one of the things that climate models are projecting are increases in temperature. Temperature is projected to go up. I'll get to observations in a moment. Temperatures are already going up as global warming continues. One of the most significant impacts of temperature effects on hydrology is changes of snowfall dynamics. You get more rain, less snow. What falls as snow runs off faster and earlier in the season. And in the western United States, the projections are, okay, I'm putting this thing down.
Trigger happy.
Yeah, it's not me, I think. It's the electrical impulses of my body or something like that. Is that snowmelt will occur, snowfall and snowmelt will occur earlier. especially in the Pacific Northwest, in the Sierra Nevada, in the Rocky Mountains, by, over time, sooner and sooner, by a couple of weeks, by ultimately a very substantial change in the timing of snowmelt dynamics. Here's a little more detail on that. These are projected changes in stream flow timing, runoff, from the decade of 2080 to 2099, compared with what's considered a typical average from 1951 to 1980. And the red circles basically show very significant shifts in the timing of runoff in the western United States by 10, 20, 30 days or more. These are very dramatic shifts in the timing of runoff. And I would note, we've built our infrastructure in the western United States, and we've built our infrastructure worldwide to deal with the climate that we already have. We built our We built our reservoirs and we operate our reservoirs under certain conditions about when we're going to get our runoff. And one of the things that climate models are telling us is that those projections based on past climates are no longer going to be useful, and we're going to have to change the way we think about and operate a whole range of things, but in this case particularly our water systems. If you integrate all of these things together, you think about changes in snowfall and time, changes in precipitation patterns, changes in runoff, you can put together indices of water stress. This is one example of water stress. It's the ratio of runoff to water use. When your water use is a very significant fraction of your total runoff, you're running up against constraints on how much water you have to do the things that you want to do, how you can meet the needs of growing populations or growing economic demands. And again, when you think about climate change, this is a graph that shows expected water stress under conditions of climate change. And what it tells us is that the western United States, which is already water stressed, is going to be increasingly water stressed. This computer has a mind of its own. Or maybe it's telling me to move on. So there are other issues associated with climate change in connections with water resources. Again, we heard a talk earlier about sea level rise. Sea level rise isn't exactly a freshwater issue, which is the focus of much of my work, but there are connections between sea level rise. Obviously, there are connections between climate change and sea level rise, and we heard many good talks about this. But there are connections between sea level rise and freshwater resources. In our coastal areas, in North Carolina, in Long Island, in parts of California, in parts of Florida, our water use comes from groundwater aquifers. We pump water out of the ground for commercial, industrial, agricultural uses. As sea level goes up, there will be more saline water penetration into freshwater aquifers. Even without sea level rise, when you pump a lot of water out of coastal aquifers, there's a risk of saltwater contamination. You pump water out, fresh water out, more salt water moves in. As sea level rise goes up, that threat will be even worse. That challenge will be even worse. And we will see more and more coastal aquifers contaminated by salt water. And for many coastal communities, their main source of water are coastal aquifers. For island nations in the Pacific, their only water resources are freshwater lenses, aquifers, that are greatly affected by sea level rise and by pumping rates. But there are other pieces to this puzzle. It turns out that this is a map, it's a little hard to see, this is the San Francisco Bay Area. At the Pacific Institute, we did a comprehensive assessment of the impacts of sea level rise on the coast of California from Oregon down to Mexico. We looked at infrastructure at risk, we looked at populations at risk, we looked at ecosystems at risk, we looked at roadways, we looked at railroads, and we looked at, for example, wastewater treatment plants. We build our wastewater treatment plants at sea level, because historically what we've done is we've collected our human and industrial wastes, we've treated them based on our federal laws to certain standards, and then we throw that water away. We dump it in the ocean, typically, if you're along the coast. For San Francisco Bay, there are 22 wastewater treatment plants at sea level within a meter of sea level that will be inundated by even a 1 meter sea level rise, which again, as we heard yesterday, is certainly within the realm of what we expect over the coming decades or the coming century. And these plants will have to be protected, they'll have to be moved, they'll have to be re-engineered. It's an example of one of the kinds of risks, this one somewhat associated with water resource management, associated with climate change. Every major airport in the Bay Area, 280,000 people, today's population live within 1 meter of sea level in the San Francisco Bay Area. $100 billion of infrastructure, in today's dollars, today's infrastructure is at risk of a 1 meter sea level rise in the Bay Area, and so on. Actually, these maps, wastewater treatment plants, police stations, health clinics, roadways, airports, population are all available on the Pacific Institute's website. And if you're interested in some ways of evaluating the risks to society of sea level rise, take a look at those maps. So those are projections. They're based on what we understand about physics and science. They're based on model estimates. But another piece of this puzzle is, what do we observe? What are we actually beginning to see? You've seen this graph at least twice this week. I could have taken it out of my presentation, but I decided to leave it in. There were 2 points I wanted to add about it. This is the ice core data on carbon dioxide. The 2 graphs you saw previously showed this graph to 400,000 years before present. The x-axis is from present to 800,000 years ago. The ones you saw basically took the ice cores down to 400,000 years. But we've extended the ice core data to 800,000 years. And you see, and it's CO2 concentration parts per million on the y-axis. And you see the natural variability of the climate. Increases of CO2 over time, decreases of CO2 over time, within a band of 180 to about 280 parts per million. And you see the current observations this is as of January 1st, but it's still about the same. The current atmospheric concentration is 400 parts per million. That puts us up here where we are today, way outside of the band of natural variability over the last approximately million years. The one other thing I put on this graph was Homo sapiens didn't appear on the planet until 100 to 200,000 years ago. I sometimes get the question, well, okay, 4 million years ago or 20 million years ago or 500 million years ago, it was a lot hotter and there was a lot more CO2 in the planet. And that's true, but we weren't around. And we didn't develop our society and our culture and our civilization and build our infrastructure for that climate. We built it for this climate, the interglacial climate. 280 parts per million, the pre-industrial level of CO2, and the temperature and the natural variability of the climate associated with that situation. We're in a different world today. This is sort of the same graph. It's temperature anomalies, actually, not CO2 anomalies, over the last 2,000 years. And it shows, again, the paleoclimatic reconstruction of temperature over the last couple of thousand years, and then added on the instrumental record from land-based, sea-based, atmospheric, satellite-based instruments showing the increases in temperature associated with our emissions of greenhouse gases. And we can look at other observations. We can look at global temperature records. Sometime in the next day or two, what's the date today? Tomorrow, NOAA and NASA are going to release their 2014 global temperature estimates. I'm not going to break their embargo, but it's warm. Okay, it's already broken. Oh, all right. But this is the temperature records for the United States, showing temperature from 1895 to 2014, the end of 2014. These data are already on NOAA's website. Showing the long-term trend, showing up and down in temperatures, but the long-term trend. We can look at precipitation also for any particular station, for the continental United States, for the globe, and so on, showing an increase in average precipitation over the last century. Not a huge increase in precipitation on average, but an increase in precipitation trends. But our observations are suggesting that climate change is already affecting water resources. Higher temperatures means more evaporation. More evaporation means more water in the atmosphere and more precipitation. That's what the models suggest, and it's what observations are already showing us. This is actually a graph, a photo from the Mississippi floods in the year 2000. Some of you may remember the Mississippi floods. So that flood in the year 2000 was considered a 1 in a 500-year flood event from a hydrologic perspective, the severity of which hydrologists expect to occur once every, on average, statistically 500 years. Unfortunately, in 1993, I think it was, there was another 1 in a 500-year flood event on the Mississippi system. Statistically, you can have two 1 in a 500-year flood events back to back, 2 years in a row, and then not have another one for 1,000 years. Nevertheless, this makes hydrologists and water managers and emergency planners in cities very nervous. This kind of change in the hydrology, and we're seeing it not just in the Mississippi Basin, but we're seeing it in watersheds around the world. Changes in the statistics of flows in rivers. The truth is also, we're not interested in average precipitation. And this audience knows this better than anyone. We're interested in extreme events, heavy precipitation events, and we're interested in local events. That's what really hurts us, and that's what we'd like to know more about. We do see changes in heavy precipitation in the United States, defined as the percent of precipitation that the amount of precipitation that falls in the heaviest 1% of daily events. We see a particularly big increase in the northeastern part of the United States, but we see it throughout the United States. We're seeing not just changes in average precipitation, but we're seeing changes in extreme precipitation events. And that's, again, something that's actually been projected by climate models and is now beginning to be observed in our record. Glaciers are disappearing. We had great talks earlier by James Balog and by others showing not just the short-term changes in glaciers, but long-term changes in glaciers. And I put this picture in here to remind me to talk about why we really care about this. Obviously, there's the aesthetics of our mountains, and that's an important issue for many. It's an important issue for me. We're heading for a world in which Glacier National Park in the United States has no glaciers, or maybe a few glaciers. I think that's maybe a teaching moment for our children, but it's only one piece of this puzzle. Another piece of this puzzle is that there are billions of people, literally, throughout the world, who are dependent on runoff from mountainous regions. The Himalayas, the Alps, the Andes. And as glaciers disappear, there are going to be, and we're already seeing, changes in runoff dynamics for the major rivers, the Indus, the Ganges, the Brahmaputra, the Salween, the Mekong. These major rivers that are fed by glaciers are going to see in the near term increases in flow, because you have this stock of water sitting in the mountains that's been there for centuries that is beginning to run off faster than it would otherwise run off naturally. And then over time, that runoff is going to decrease. And then the changes in the timing we're going to see changes in the timing as we move from a snow-driven system to a rain-driven system. And that's part of another reason why we actually care about glacier dynamics. But what about extreme weather events? This is your world more than mine, but this is an image from what we call atmospheric rivers. We used to call them Pineapple Expresses. It turns out that water delivered to the western coast of the United States and to California comes in storm events. It comes from our rainy season is October through April. That's our water year starting in October. We don't get a little bit of rain throughout that rainy season. We get significant events. We get storm events. We get what are now called atmospheric rivers. This is the atmospheric river that hit California a few weeks ago in December. We were delighted to see it for reasons I'll talk about a little bit later when I talk explicitly about the California drought. One of the remarkable things about this particular event, from my perspective, was how far in advance it was forecast. You guys have a difficult job. I understand how hard it is. The previous talk talked about the difficulties of projecting snowfall several days in advance. The Pacific is really tough from a weather forecasting perspective. I understand that. We have far fewer instruments observing the dynamics of weather events off the Pacific are very difficult. This event was forecast way in advance, and it was incredibly accurate. When it was coming, where it was coming, how much water was going to deliver, and it helped water managers prepare. It helped us prepare to operate our reservoirs a certain way. It helped the cities prepare for flood events. It was a great forecast. Thank you very much. But we see this regularly. This was a big storm event that hit California in January of 2008. This is Hurricane Sandy. And again, there's been a lot of discussion about forecasting hurricanes, the challenges of forecasting track, strength, persistence, and so on. But I wanted to put a picture of Hurricane Sandy up here for a couple of reasons in the context of climate change. And I'm going to talk more about this in a moment, about causality versus influence. But Hurricane Sandy hit New York at high tide. The impacts obviously would have been less if the storm surges had hit at low tide. That's serendipity. That's just the way the world works. Obviously, the damages were far more extreme. The storm surge impacts were far more extreme in a storm that comes at high tide than one that comes at low tide. But there are two other issues at play here. One is that the tide, sea level, is 9 inches higher today than it was 100 years ago. And that has an effect, an influence on the damages of storms that we experience. Another is that sea surface temperatures are hotter now because of climate change than they were 100 years ago. And sea surface temperatures have an influence on hurricane strength and storm strength. And so there's an influence, an increasing influence of climate change on these kinds of extreme hydrologic events. And figuring out how to integrate that into our models and into our risk assessments and into our risk communications for the public is a new challenge facing many of us. So I'm going to argue that extreme events are increasingly influenced by climate change, and I've highlighted the term influenced here. This is 30-day precipitations and 30-day percent of normal precipitation for May of 2011. And this was the big precipitation event that caused some flooding on the Mississippi Basin. And you can see if these numbers are pretty extreme. These are 600% of 30-day precipitation. This was an incredibly intense series of precipitation events. But I would also note, at the same time, we had this period that most people were focused on what was going on here in the Mississippi Delta, in the Mississippi Basin. But we also had this was the time when the Texas drought was particularly significant, when the drought in the southwestern U.S. was significant, and when we were beginning to see drought in California, where we were getting no fraction of normal precipitation in other parts of the country. We're beginning to see more and more of these extreme events. I do want to note that the impacts of extreme events are not just based on the condition of the climate or the condition of the weather. They're obviously based on population, how many people live near the coast, the kinds of infrastructure we build. Ultimately, the risk of extreme events for hydrology depends on not just the climate and the weather, but on the systems we put in place to deal with the climate and the weather. This is a map of population projection by county from expected population increases from the year 2000 to 2050, showing actually decreases in population in the central part of the U.S. over the next few decades, increases in the western U.S. and in the eastern U.S.
What is that map made with?
Which one? This one?
Yes.
This comes from the U.S. Global Change Research Program. The U.S. GCRP put out a report on global climate change in 2014, and it had not just information about climate dynamics and what we expect, but some information about population projections as well.
It was one of the fastest
Yeah, okay, so this is a projection. North Dakota is growing very rapidly right now because of the economic advantages of fracking. This doesn't take account that kind of dynamic, and I couldn't tell you whether fracking is going to continue in North Dakota over the next 50 years or so, but that's a factor. And these factors change over time, and ultimately, population projections and where people choose to live affect the risk that we experience from, for example, sea level rise in coastal storms or heat stress in our cities or so on. Those are all important factors.
In the plains here in Kansas and Nebraska, is that influenced by the Gleick aquifer and the lack of pivot irrigation and agriculture? Is that what it's based on, that outflow?
It could be. I couldn't tell you. The question was, is the drop in population in the central part of, the projected drop in population in the central part of the Great Plains due to the water challenges we face with the Ogallala aquifer? I will talk about groundwater shortly. I'm not sure why these projections, my guess is these projections were based on trends, maybe some economic assessments about economic growth in these regions. Like all projections, take them with a grain of salt. That's probably the best way to put it. Munich Re was also mentioned, I think, in Admiral Titley's talk earlier in the week. Munich Re is one of the world's leading reinsurance companies, and they've noted, quote, "The only plausible explanation for the rise in weather-related catastrophes is climate change." They care about this because this costs them money. They spend a lot of time thinking about causality, about long-term projections, about what their insurance rates ought to be, and they see the trend in climate-related impacts to society. But I want to go back for a moment, a digression to this issue of causality versus influence. And maybe I'll, no, I won't. There's been a big debate about this in the media recently, in the science community recently. There's the question about whether climate change is causing an extreme event like Hurricane Sandy has been a topic of conversation. I think that's the wrong question. Causality is a really difficult thing to prove. We have hurricanes in the Atlantic all the time. We can't say that climate change is causing a particular hurricane. And I just think, as I said, I think it's the wrong question. I think the question is influence. We know the climate's changing. We know that temperatures are going up. We know that sea levels are going up. We know that sea surface temperatures are going up. We know that precipitation patterns are beginning to change. I think the question is influence. And I would argue that there is rapidly growing evidence from a combination of basic climate science, models, and real-world observations that human-caused climate change is influencing extreme weather events. And the Hurricane Sandy example is an example of that. No one can argue successfully that Hurricane Sandy was caused by climate change. But we have the influence of sea surface temperatures, the influence of rising sea levels, affecting events that may otherwise occur because of natural climatic variability and weather variability. So let me talk about vulnerabilities and why we care about these things. And I'm going to do it in the context of fresh water, which is my particular focus. But obviously, society is vulnerable to a lot of different things. We're vulnerable to heat. We're vulnerable to storm events. We're vulnerable to air quality challenges associated with weather and climate. But I'm going to focus on water. And let me first make the comment that we've spent billions, if not trillions of dollars worldwide building water infrastructure to store water in wet years so we can use it in dry years, to build dams so we can prevent floods, to deliver water from a wet area hundreds of miles or more to a dry area, to treat water to the quality that we really want. We've built a vast, complicated set of water infrastructure based on the assumption that the future climate's going to look like the past climate. And if there's anything that we should get out of the work that we're all doing, it's that that assumption is no longer true, and that this infrastructure is vulnerable to a changing climate. And I'm going to give you a couple of case studies. I'm going to talk about California, and then I'm going to talk a little bit toward the end about this issue of water and conflict in the context of the California drought. This is today's drought monitor. The drought monitor, many of you know it, but it's updated weekly on Thursday. This is today's update for the California drought monitor. The drought monitor is basically a measure of overall soil moisture based on something called the Palmer Drought Severity Index. And 100% of California is in drought, some degree of drought. The categories of drought are abnormally dry is the lightest color of yellow. Moderate drought is a little darker. Well, I guess there's a little change in intensity of yellow. Severe drought is in this shade of yellow. Extreme drought is this red. And extraordinary drought is this dark color. And the table on your right shows the percentage of the state that's in each of those categories. 100% of the state is in one of those categories of drought. And I would just note in the last week, this shows current, last week, 3 months ago, a year ago. A year ago, 98% of the state was in drought. The truth is California's been in drought for 3 years now, and I'll come back to that in a moment. But the category of extreme, I guess, exceptional drought has gone up. More of the state this week than last week is in exceptional drought. So in fact, the drought is continuing even though this is the wet season in California. Basically 39%, 40% of the state is in exceptional drought now. Quick question?
Brad Panovich, NBC Charlotte. I hear a lot of people, especially hydrologists and people that deal with drought, they don't like the Palmer Drought Index or they don't like the Drought Monitor. And like in the Southeast, the state of North Carolina and like Duke Power and NOAA, they all use like different parameters for what they consider drought. I mean, which one do you prefer, and do you see issues with all these conflicts?
Yeah, that's a great question. There is no single definition of drought. I should have started with that. Some people think of drought as a precipitation deficit. Some people think of it as an index that measures some combination of soil moisture. Some people think about it in the context of there's not enough water to do the things that we want to do from an economic or a societal perspective. I like different kinds of indices for different kinds of measures. I love the drought monitor, not because I think the Palmer Drought Index is a perfect index, but because it's a long-term, consistent way of thinking about trends in water availability for soils, which is one of those measures. But there are lots of measures of drought. In fact, there's been an interesting debate in the climate and meteorological community about the California drought and how bad it is, and I'll talk about that in a moment. But this is today's drought monitor. California's still in a bad drought. Here's another index. This is just the average California precipitation. This is actually 24-month average precipitation from over the last 2 years, ending in December 2014. And it shows variability. It shows wet years and dry years from 1895 to 2014. Wet years, dry years, some really wet years, some really wet years, and 2014, actually the last 24 months of average precipitation, 2013 and 2014, is the driest 24-month period in the California record. So if precipitation is a measure of drought, it's dry. It's really dry. Here's the 76-77 drought. For those of you from the western U.S. know that was the driest 2 years on record before the current drought. But drought's not just precipitation. Drought is also affected by the demand for water, and the demand for water is also affected by temperature. This is the same graph for temperature, 24-month, 2-year average temperature for California from 1895 to 2014. The last 24 months in California have not only been hot, they've been extraordinarily hot. And in fact, you can see a trend here. This is global warming, this trend, I would argue. But by any measure, global warming or not, the last 2 years have not only been dry, they've been hot. And The demand for water in California is affected not just by how much water we have in our reservoirs and in our soils and in our rivers, but by temperature. And I'll come back to that in a moment. And if you put these things together, this is an anomaly graph. It shows temperature anomalies in degree F. So each of these dots is a year over the last 120 years, from 1895 to the present. Any dot above this x-axis line is warmer than average over the 1900 to 2000 average temperature. Anything below it is cooler. So these are cool years, warm years. And this is precipitation anomalies. Anything to the right of this y-axis is a wet year. Anything to the left is a dry year. And all of the years are plotted. Here's 2014. It shows how extreme 2014 is in this suite of anomalies over the last 120 years. So hot and dry. So how, again, is this a bad drought? Is it the worst drought on record? Is it the worst drought in the instrumental 120-year record? Is it the worst drought in 1,200 years? There's a field, paleoclimatology, a lot of the work that's done to evaluate past climates on the Earth, the last 800,000 years of CO2 that I showed you. We look at tree rings in the western United States as a way of measuring water availability and Palmer Drought Index. There was a paper published last year, late last year, that looked at the 2012 to 2014 three-year drought in the context of the paleoclimate record over the last 1,300 years, for which we have some sense of drought in California. And again, there's variability. We have extreme droughts in the past 1,200 years. Actually, this is 1900 to 2000. This is the year 800 to 2014, showing that by some measures, the current three-year drought in California is the worst in 1,200 years in California. Worst, not necessarily the worst. It doesn't really matter to me. It's a bad drought. But in the context of what we understand the natural variability of climate to be, this is a particularly bad drought. Before I get to the next slide, it's also obviously bad because today we have 38 million people living in California. It gets back to this question about population. We had a bad two-year drought in 76 and 77, a terrible two-year drought in California. There were, I think, 13 million fewer people living in California in 76 and 77. The population of California is growing very, very rapidly. So if you have a drought in 76 and 77 and the same precipitation and water availability, but with 17 or 18 million more people, the drought is worse if you aren't looking just at the meteorological conditions, but you're looking at economics and population as well. So in order to evaluate some of these risks of extreme events, I'll just reiterate, we don't want to just look at the climate and the weather. We want to look at human infrastructure and population as well. Now, there's a big debate about this drought. Is this linked to climate change? Is this drought, I'm not going to say caused by, because I think that's the wrong issue, but influenced by climate change? And there are lots of ways of thinking about that puzzle. Some of you may know the recent debate about what's been nicknamed the ridiculously resilient ridge. This is this 500 millibar geopotential ridge that formed over the North Pacific, the Gulf of Alaska, and basically diverted a lot of the moisture that normally would have hit the western United States and California north. It's related to a lot of the cold temperatures in the eastern United States and the changes in the jet stream. And there's been some conversation about not just the formation of the ridiculously resilient ridge. This is actually from February last year, February of 2014. But whether or not the formation and persistence of the ridge had anything to do with dynamics of sea ice melt in the Arctic. And Jim, maybe you could comment about this more than I, but there are some scientific papers now out that are suggesting that this kind of pressure formation and system is more likely with an Arctic that is warmer and more ice-free than otherwise. And there's obviously a connection there with climate change. And I would just note, this is yesterday or a couple of days ago. This ridge is reforming, it appears, and there's some question about whether it will continue to contribute to the California drought or to temperature dynamics in the eastern part of the United States or to changes in precipitation patterns in the rest of the United States. So that's one question, and there's some evidence that these pressure systems could be connected to changes in the Arctic. We also know that precipitation in the western United States is very dependent on sea surface temperatures in the Pacific, El Nino, La Nina dynamics. El Nino years, we get much more precipitation in Southern California than in La Nina years. Last year was sort of an ambiguous El Nino year. It looks like a new El Nino is forming. Some people are hoping that'll mean more precipitation in California. But there's also been some work to try and evaluate whether or not changes in sea surface temperatures over the last 50 or 80 years have influenced the recent drought and the probability of drought in California. And at the moment, that science suggests no, they don't see a link between changes in sea surface temperatures and the current dynamics of the drought in California. So that's another piece of the puzzle. And this is a map of sea surface temperatures for January of 2014. The third piece of this puzzle, though, gets back to this question of temperature. As I showed you, the last few years of temperature in California have been extraordinarily high. The same precipitation pattern in California with a high temperature causes a worse drought than a precipitation pattern with a low temperature. Higher temperatures means more evaporative loss from our soils. Higher temperature means more evaporative loss from our reservoirs, which store water in the winter so we can use it in the summer. And higher temperatures means more evaporative demand from crops. And 80% of the water in California goes to grow crops. I'll come back to that in a moment as well. So whatever you think about the ridiculously resilient ridge, whatever you think about sea surface temperature dynamics in the Pacific, higher temperatures alone have made this drought worse than it would otherwise have been from purely a precipitation point of view. And so that's another example, I would argue, of the influence of climate change, if one believes the higher temperatures are associated with climate change, on extreme hydrology and on water. A little bit of background for California water. I already mentioned this a second ago. 80% of the water humans use in California goes to agriculture, and 20% goes to urban water use, urban being residential, commercial, industrial, institutional water use. For urban water use, this pie chart shows urban water use, a little hard to read, but the vast majority of urban water use in California is the water we use in our homes. It's residential exterior, outdoor on our lawns and gardens, residential interior, toilets, washing machines, showers, dishwashers, the stuff we use indoors. Together are about 65% of urban water use in California, and the rest is industrial and commercial and large landscapes that are institutional, golf courses, that kind of thing, and other. That's where our urban water use goes. And these circles are per capita urban water use, the amount of water used per person in different regions of the state. And you can see in our coastal, cooler areas, per capita water use is smaller than in our inland, hot, Central Valley, Southern California locations, where lawns are bigger, outdoor landscapes are more consumptive of water, and so on. There's a lot of dynamics about water use in California. I won't get into the politics of water use in California, but they're even more complicated. Jim, yeah.
So these are home uses of what agriculture is not mixed into in any way.
That's right.
Okay.
The question was, are these per capita water numbers only urban use, or do they include the agricultural water uses included? And they're only urban. This is urban water use. 170 gallons per person per day for urban water use, which is residential, industrial. It's not just home, but it's water used in our urban centers. And some of these water agencies down here use a huge amount of water for reasons I won't get into. So when we have a drought, what happens? Well, let me back up. What happens for agriculture? Again, agriculture is 80% of our water use in California. They tend to be cut off first. We don't have the problem yet in California where in my home I turn on the tap and nothing comes out. That would be a wake-up call. But our urban water availability tends to have a higher reliability than agricultural water use. Agriculture pays less for it. They're more vulnerable to drought. And what happens during a drought is we see reduced surface water deliveries. When we don't have the water in our reservoirs and our rivers, there's less water to deliver to farmers. And last year, some of the major water systems in California, the federal systems and the state systems, delivered zero water to some of their users. It varies, depending on water rights, depending on location, but some farmers got zero surface water deliveries from the big infrastructure that we've built in California. When less water is delivered on the surface, farmers go to groundwater. We have almost no restrictions on groundwater pumping in California, which is another issue I won't get into, but what that means is that farmers can turn to groundwater if they can afford to drill a well, and there is massive groundwater overpumping in California. And it's related to this question earlier about the Ogallala Aquifer, where we also see overpumping of groundwater in the Great Plains. And here is a graph, a map, that shows for the Central Valley of California. Here's the Bay Area, Los Angeles is down here. This is the Central Valley of California, which is where the big agricultural production occurs. Here's Sacramento, Stockton, Merced, Fresno, Bakersfield down here. The red is, the colors show groundwater level, changes in groundwater levels from 2013, spring of 2013 to the spring of 2014. And the redder it is, the greater the drop of groundwater. When you pump groundwater faster than nature recharges it, groundwater levels drop. It's like a bathtub. You have inflow and you have outflow. And if your drain is open, which is groundwater pumping, and there's not much coming in from rainfall and runoff, groundwater levels drop. Your bathtub levels drop, water levels drop in the ground. And in some parts of California, especially the southern part of the San Joaquin, we have massive drops of groundwater, 30, 40, 50, 60 feet in drops of groundwater. Wells are going dry. Farmers are having to drill deeper wells. They have to put stronger pumps. This is an economic cost to them. And I would also note that when we have an average year in California, in rainfall, we have overpumping of groundwater. Our system is not in balance. Even in a normal year in California, a normal hydrologic year in California, we have overpumping of groundwater. That's a water management problem, but it's an indication of the severity of the mismatch, and I would argue the growing mismatch between water demand and water supply. We fallow. When there's not enough water, if farmers can't get water, they can't grow. This year, the estimate is that about 10% of the ag land in the Central Valley was fallowed. That's not a huge impact yet because farmers have been overpumping groundwater. They've turned to groundwater and they've made up the loss of surface water. But the more fallowing, the more economic impact there is on farmers. And that's another response to drought. They switch crops. Instead of growing water-intensive alfalfa, they may plant more permanent crops that produce more revenue to them and are less water consumptive. And we've seen over the last several decades in California a very significant shift in crop type from field crops to permanent orchard crops, fruits, nuts, vegetables. There's been a lot of conversation about almonds in the media. We produce a lot of almonds, but there are a lot of very high-valued crops grown in California. And California is responsible for some of the grows crops that are grown nowhere else in the United States. One of the problems with going from field crops to permanent crops is that a field crop you can fallow in a dry year. Permanent crops, you have to water those trees even if there's a drought or they die. That's a 20-year investment. And so that's a dynamic that we're beginning to wrestle with too, the priority of what we spend our water on. They go to improved water use efficiency. They move from flood irrigation to sprinklers, or from sprinklers to precision drip. And we're beginning to see changes in all of these pieces of the puzzle for water use, not just in the face of drought, but in the face of long-term complications with Western water in the US. But drought doesn't just affect agriculture. This is a graph of the anomalies of hydro generation from the year 2000 monthly to the end of 2014, actually to October 2014, the end of the water year in California, in terms of megawatt hours per month produced. And basically, if we're below this line, you're producing less than average hydropower in that month. If you're above it, you're producing more than the average hydropower in this month over this period. And what you see here is the last 3 years of drought, where hydropower has been cut. There's not enough water to run the turbines, and we've lost, on the average, $2 billion over this period to consumers who had to pay more for more expensive natural gas. When we don't produce hydro, we go to our marginal energy source. In California, the marginal source of energy is natural gas. It's more expensive, and consumers pay that difference over expensive natural gas versus cheap hydro. There's another interesting thing here, which is that this is the 3-year drought. But in fact, one could argue we're not in a 3-year drought, we're in a much longer-term drought. 2007 to 2009 was a dry year in California. We happened to have a couple of wet years in the middle, and that recharged our reservoirs, but there's a cost to California of drought, and hydropower is one of them. Food, energy, I could talk about ecosystem impacts and so on, but drought has severe impacts on society. Let me move to my last case study, and that is the connection between water and conflict. Another thing we do at the Pacific Institute is we look at, about half of our work is international, we look at the connections historically between water resources and violent conflict. I'm going to talk a little bit about how water might lead to conflict, how water issues have led to conflict, causality, a little bit about trends and factors, and then I'm going to talk about a specific example in the context of Syria. We maintain a website if you're interested in history. If you just Google water conflict chronology, you'll find it, or if you go to worldwater.org, you'll find it, where we have a list of historical conflicts over water. We have a timeline, we have a map. I'll show you the map now. This is the water conflict chronology map. This maps conflicts going back to 2500 BC, 4,500 years or so of conflicts over water. Each one of these is a conflict. If you click on them, you get information about the date, the parties involved, the kind of conflict, a citation and reference to where you can get more information about the conflict. There's a long history of conflicts over water, going back thousands of years. We fight over access to water, as in, I want your water. We use water as a weapon in conflicts that start for political or religious or ideological reasons. We attack water systems during conflicts. There are unfortunately growing examples of the connections between terrorism and water resources. But there's a long history of conflicts. And on this map, you can sort by region, you can sort by the type of conflict, you can sort by date, you can search for particular examples. But there are examples all over the world. This is a graph that shows conflicts, the number of conflicts in the conflict chronology database from 1931 up until the present, actually till the middle of 2014. We haven't added the last few months. And it shows over time an increase in reported conflicts over water. A very significant increase in conflicts over water. I actually think there are two things going on here. One is, I think the reporting has gotten better. I think there's a reporting problem. Today, if somebody is killed in a fight over water in West Africa, I hear about it a few days or a few hours later. It's online. I think we probably missed lots of conflicts in this period of time when media was less engaged in this or there was less access to this sort of information. But I also believe there's a real change in conflicts over water. I think we are seeing a real increase in disputes over allocations of water, over management of water, attacks on water systems, and so on. Parsing out those distinctions, what's a real change, what's a reporting change, I think still has to be done. But there are more and more reported conflicts over water internationally. I could show you the same graph for interstate conflicts, that is between two nations, India versus Pakistan, Turkey versus Iraq versus Syria, compared to intrastate conflicts, which are between ethnic groups, pastoralists and farmers in Africa, which is an example, between two states in India, Karnataka and Tamil Nadu, which is an intrastate conflict where people have died over allocations of water between two states in India. And it seems like there's a growing increase in these intrastate conflicts, not between two nations, but these subnational conflicts. And there are reasons for that, one of which I think is our tools are better for reducing the risks of international conflicts. Diplomats get involved, we have treaties and so on, than these intrastate conflicts. Here's the Jordan River Basin. This is a hard graph to see, hard map to see, but here's Lebanon, here's Syria, here's Jordan, here's Israel, here's the West Bank. Here's the Jordan River right here, and the Yarmouk River, which is the border between Jordan and Israel and Syria, and the upper reaches of the Jordan River. There are three tributaries to the northern part of the Jordan River, the Hasbani, which is in the Golan Heights, which is shared by Israel and Syria, depending on your politics. The Litani, which is in Lebanon, arises in Lebanon, and the Banias, which is entirely within Jordan. The Jordan River flows past Lake Tiberias, and it flows ultimately into the Dead Sea. The Jordan River is not a big river by any measure. And 100% of the water of the Jordan is now consumed. In the lower part of the Jordan Basin, it's also shared by the Palestinians in the West Bank. The lower part of the Jordan Basin, you can walk across the Jordan, even if you're not Jesus. And it's a place where there has been conflict over water for thousands of years. There's no agreement about how to share the waters of the Jordan. It's entirely consumed. The politics is already complicated, and there are many examples in the water conflict chronology where water has been a source of conflict, where there's been attacks on water systems, where water availability and disputes about allocations have led to violence, and so on. But let me talk about Syria now. I wrote a paper that was in the journal Weather, Climate, and Society last year of the American Meteorological Society, looking at this issue of water, drought, climate change, and conflict in Syria and the connections here. The conflict in Syria is a complicated one. It's a religious conflict. It's a political conflict. It has factors related to population. It has factors related to economics. It has factors related to water as well and to climate. And this paper, you can get the paper from the AMS, talks about all of the different pieces of this puzzle. And let me just talk about 4 of the pieces of the puzzle. This is a graph that shows runoff in the Euphrates River. The Euphrates starts in Turkey. I should have had a map maybe. The Euphrates starts in Turkey, crosses the Turkish-Syrian border, flows through Syria, crosses the Syria-Iraq border, flows through Iraq, and then ends up in the Arabian Gulf. This is a graph that shows the flow of the Euphrates River at a gauging station called Drought, which is in Syria just below the Turkey-Syria border. So it's the flow of water into Syria from Turkey from 1935 to 2010. And what it shows is the variability of a dry region river, wet years and dry years. And it shows the long-term decline in water availability to Syria on the Euphrates River. And if you look at the population of Syria and Iraq, the populations of those countries are entirely next to these rivers, the Tigris and the Euphrates rivers, because these are very dry countries. It's like the population of Egypt is entirely in the Nile basin, within a few miles of the Nile. So the drop in flow on the Euphrates River is a serious challenge for Syria. The drop in flow in the Euphrates River is the result of a number of factors. Largely, Turkey has built some massive water infrastructure in southern Anatolia on their side of the border, and they are extracting more and more water out of the Euphrates for agricultural production. So there's a human component to this drop in flow. But there's also a climate context as well, which I'll come to in a moment. But population's also a key issue in the dynamics in the Syrian conflict. This is the population of Syria from 1950 to 2012. In 1950, the population of Syria was 3 million. In 2012, the population of Syria was 22 million. No change in water availability, or actually a decrease in water availability. You just cannot meet the needs of a growing population like this without economic, political, and social stresses. So population is a factor, and some of the previous talks talked about population. Water management is a factor. These are graphs that show I forget what year, it's probably 2010 approximately. Syria is an agricultural economy. It shows the irrigated area and the percentage in irrigated area, irrigated by flood irrigation, sprinkler irrigation, and precision sprinklers. So you can see that the vast majority of the agricultural land in Syria was irrigated with very inefficient, water-intensive flood irrigation. And so that's a water management challenge. And then the final component of this is, it turns out there's been a long-term trend decrease in winter precipitation, which is the wet season precipitation for the Eastern Mediterranean, over the last couple of decades. A trend that climate scientists argue is beyond the range of natural variability and that is linked probably to climate change. If you put these things together, you have religious and ethnic tensions. You have a decrease in water availability and flows in the river. You have a decrease in precipitation in the region. You have inefficient management. And what happened in Syria, starting in about 2007, was a severe multi-year drought hit the region. There was not enough water for agricultural production. Millions of people moved from the rural agricultural areas to the major cities in Syria, some of the cities where the ethnic unrest first unraveled in 2009 and 2010, and the subsequent civil war. Admiral Titley earlier talked about the Arab Spring. There are strong connections between our vulnerability to water resources and politics. I don't think we'll probably fight over water in California in a violent sense. We use lawyers instead. But understanding these connections. Yeah. Okay. So you've provoked me. I'm going to go back for a moment. A slight digression, Jim. Thanks. It's your fault. In the 1930s, California wanted to build a big dam on the Colorado River called Parker Dam, so it could extract water to divert from the Colorado River, shared by Colorado, Utah, Wyoming, New Mexico, Arizona, and California. Did I include Nevada? 7 states wanted to divert water from the Colorado River to the big population centers, the growing population centers of Southern California. Arizona rushed its National Guard to the Arizona-California border, which is the Colorado River, commandeered 2 ferry boats, mounted machine guns in the front of the ferry boats, and patrolled up and down the Colorado River for a couple of weeks. They called it the Arizona Navy. It's actually in our chronology. No violence actually occurred. Nobody was hurt. It was ultimately resolved by political negotiations. Parker Dam was ultimately built. There was an agreement about allocations of water over the Colorado, which some people still don't like. But we tend to move toward diplomatic solutions when we can. Syria didn't go that way. And again, I'm arguing that water was a component of that, not necessarily the leading component, which was, I would argue, dynamics of politics and religion, but it was a component. And the more we understand about these dynamics and these risks, the more likely we are, hopefully, to proactively work to reduce those risks. So, what do? I'm sort of going to take off my science hat here, and you know, scientists have opinions as well. I'm going to argue that continued delay in taking action on climate and on emissions of greenhouse gases means that the ultimate impacts that we experience of climate change are going to get worse and worse over time. And it's going to lead to unavoidable, more costly adaptation. A 600 part per million CO2 climate, as Jim talked about, is a very different world than a 400 part per million climate. And we're at 400 now, we're blowing past 400 and we're heading to 600. And there's been calls to restrict it to 350, which would mean cutting back on atmospheric CO2 over time. I don't know where we're going to end. But the longer we delay in taking action, the worse will be the impacts and the more costly will be the adaptation. And Howard asked a question at the very first day in the context of Admiral Titley's talk about the threats we're facing in terms of terrorism and ISIS. Immediate threats versus long-term threats. And that's a difficult dynamic for all of our cities to deal with, our politicians to deal with, our public to understand. And one of my comments about that is that, first, I think we can do more than one thing at a time. I think we can deal with immediate threats and long-term threats. But I also think we have to, and think about it in the medical context. Suppose you have a very difficult chronic disease, cancer, or some horrible long-term thing that you have to deal with, and you break your leg. Obviously, you deal with the acute challenge, but you don't stop dealing with the long-term threats to your health. And I would argue that we have to deal with short-term weather variability and climate change, but we have to deal with the long-term issue of emissions of greenhouse gases in order to deal with those long-term worsening consequences of climate. And that's an opinion, but I think it's the reality that we're facing. Interestingly, water managers are thinking about this as well, and it's sort of distressing to me how long ago this was. There's a group called the American Water Works Association. It represents 50,000 or 60,000 water utilities around the United States. And I was on a panel with them 17 or 18 years ago now, looking at climate change and the risks. And they put out a report, a white paper on climate and water that said, quote, while water management systems are often flexible, water agencies should re-examine water systems designs and operating rules under a wider range of climatic conditions than traditionally used. End of quote. Really, what they're saying here is don't assume the future climate's going to look like the past climate. You can't build your systems and operate your systems without thinking about the changes that are coming. And this gets to modeling, observation, forecasting, and so on. This is really hard for water managers to deal with. There's risk associated with changing the way they operate reservoirs. They get penalized if they get, sort of like you guys, if they get it wrong, the public's really unhappy. And so designing systems and operating systems is a difficult dynamic, but there's a move in the water management system, water management community now to try and do things a little differently, to try and integrate model forecasts in new ways that reduce risks rather than increase them. Traditionally, we've built infrastructure. The traditional response for water systems, if we move water from one place to another, we build a dam, we focus on water supply, and that's brought enormous advantages to us. But I would argue we're entering a world of what I call peak water, and I wrote a paper called Peak Water a few years ago that defined what that meant and how we have to manage it. But basically, I think we need some new strategies. We have to rethink what we mean by supply and demand. Supply used to mean tapping another river, drilling another groundwater well. As we reach the limits, for example, in the western United States of our groundwater availability and our surface water availability, there are some new supply options. Treated wastewater. I talked about sewage systems. We collect our sewage, we treat it, and we throw it away. We can treat wastewater to any standard we want, including potable water. I think we need to think about wastewater as an asset, not a liability. It's a new source of supply. Desalination is a potential new source of supply. 97% of the water on the planet is salt water. Too salty to drink, too salty to use to grow crops. But we know how to take salt out of water. It's expensive. There are environmental issues associated with that. But that's a potential new source of supply. But the other piece of this is demand. If we can grow more food with less water, that reduces pressure on our system. Move to sprinklers from flood irrigation. Yields go up, water demand goes down. If we can wash our clothes with efficient dishwashers, efficient washing machines, or wash our dishes with efficient dishwashers, that reduces the demand for water and it reduces the pressure on whatever supply we have. And we do those things during droughts when we're forced to, but if we do them in the long run, it reduces the pressure on the system. So there are supply options and there are demand options that we could think of. We need to think about food, water, energy, and climate together. So I mentioned during a drought in California, hydropower production goes down and we burn more natural gas. That produces greenhouse gas emissions. If instead of burning more natural gas, we produce more electricity with wind systems and with solar systems, you can still meet your energy demands by while still reducing your carbon emissions. Those are options. And in fact, I should have shown this, but I'm not going to. Solar and wind electricity production in California is going like this. It's on an exponential up curve because the costs are now becoming competitive with fossil fuels. So integrate food and water and energy, all these issues together, and you do things differently from an institutional perspective than you would otherwise do separately. Virtual water transfers. I don't know if you're familiar with the term virtual water, but you probably know about water footprints or carbon footprints, the amount of water or carbon embedded in the production of the goods and services we produce. It takes water to produce goods and services. So how much water is embedded in your hamburger? You often hear about that. Or how much water does it take to make the cotton that goes into, to grow the cotton that goes into your shirt? We're starting to calculate our water footprint and our carbon footprint of our choices. It turns out we move water, massive amounts of water, around the planet. Not as water, but as goods and services. We don't move water, we move grain. We grow the water here, we ship grain overseas. It takes 1,000 tons of water to make a ton of grain. That's just how much water it takes to grow grain. So when we export and import goods and services, we're exporting and importing water. It turns out there's an interesting policy debate going on now about our virtual water footprint and moving water from one place to another. There was an article that appeared in the papers a few months ago. Somebody was complaining about the water California exports in alfalfa to China. We're in a drought, this person said. We export alfalfa, water-intensive crop, to China. There's a lot of water involved there. Why are we doing that? All right, that's a reasonable question to ask. It turns out when you actually run the numbers, we import a lot more water from China in the goods and services that we consume in California than we export. So we're actually a virtual water importer. But there's an interesting policy debate going on about that. Economics, the price of water. There's a lot of talk about if you priced water properly, we would invest in efficiency. We would reduce the risks that we face by moving toward more efficient use. Higher valued consumers would buy water from lower valued consumers. there's an argument to be made for smarter economics, applying smarter economics in our water management. And then we should change our institutions. I won't get into water politics and water law and water rights in California, but the truth is we built a water management system based on 19th century climate, 20th century technology, and we're facing a 21st century world. And we'd better think about changing our institutions as well. My last slide in terms of some adaptation strategies for climate and water. We have to integrate and coordinate mitigation and adaptation measures. Let's think about greenhouse gas emissions, the water required to produce energy, the energy required to produce water, and maybe we can reduce emissions while reducing risks from our water systems. Let's evaluate the potential for existing policies to prepare for unavoidable impacts. How do you operate the existing reservoirs? How do you deal with the existing kinds of infrastructure? But we'd also better think about what doesn't work. What are we doing today that doesn't work under new conditions that might require us to then rethink economics, technology, institutions and politics, the regulatory system and the educational system? We have to communicate with the public. This is what you guys do every day. Communication is vital about what we know, about what we don't know, about what we ought to do. There are many water-related risks. We're still failing to meet basic human needs for water and sanitation for a lot of people on the planet. We have to deal with that. We have to grow enough food to meet the world's population's demand for food, and that takes a huge amount of water. That's a water challenge. We want to protect ecosystem health and human health. We built our water system in the 20th century without really thinking about ecosystems. We now know that was a mistake, and we're trying to fix that. But figuring out the connections between water and human health and ecosystem health is part of the 21st century challenge. There is a link to conflict and violence, and figuring out how to reduce those risks is important. Extreme events factors into all of this, and there's a lot we don't know about extreme events, but we're learning more and more. And frankly, this link between climate and weather is one of the most exciting scientific questions facing this community now. How do we understand those connections? And then how do we deal with the challenges of unavoidable climate change? It's time for the scientists, it's time for the public, it's time for policymakers to step up and try and understand and try to discuss the strategies for reducing these risks. Thank you very much.
Peter, as you take a drink of water, that was an excellent presentation. I think you've really opened our eyes on additional water issues. And I'm just wondering, I'd like to throw a question out to the audience and for everybody to just think about, as your roles of television meteorologist increase, to talk about climate impacts and things like that. Maybe you could think about doing some stories on the impacts of water and whether or not water is available, what kind of things are at risk if you have, if you're in a market that's near sea level. Start talking about these things so you can come out and make sure that you are the leaders in your market for addressing changes in climate, changes in extreme weather, how you're being impacted. It's not just about the wind barbs and the 1050 highs and the coastal lows, and I know that's the majority of what you have to do, but how can you perhaps step out of that comfort zone and start to lead your market in areas where your viewers will really appreciate it down the road? So we'll start off with some more questions. We have some hands in the room. We can start off with you, Jim, and then we'll... Pardon? Okay, you have two hands. We'll be right back to you, Dale, in just a second. So let's go ahead, Jim.
Peter, excellent talk. Thanks so much for coming. You brought up this issue of influence versus causality. Mm-hmm. There's certainly I guess a growing discussion among climatologists where some people argue that because there's additional greenhouse gases in the atmosphere, because there's more energy in both the atmosphere and the ocean, the baseline has changed, and any weather event that occurs in that changed environment must have some influence by that changed environment. How do you feel about that?
I actually feel that way. I think the evidence is clear that we've changed the climate. Because the weather is the short-term manifestation of the climate, I think there is always going to be influence of a changed climate on weather. That doesn't mean it's necessarily going to make the weather worse. It could make the weather better. Again, it'd be nice if wet areas got a little drier and dry areas got a little wetter over the long term. If you're in a really cold area, I understand it's a little warmer now. Well, that may not be a bad thing. So I'm trying not to make a value judgment on good versus bad, but I do think there is now influence of climate change on our weather.
Paul Goodlow, Weather Channel.
Yeah.
I know you don't want to talk about the politics, but the water rights in California. So some farmers, it's either use it or lose it, and that makes no sense in terms of conserving water in a drought. Is there any hope in kind of changing these and making it more efficient where, in times of plenty, sure, you can have your allotment, but even in times of plenty, just use what you need without the fear of having those rights taken away because they have not used their allotment?
So you've touched on really one of the most difficult challenges of Western water, and especially California water, which is how we allocate it. We have a water rights system in the West based on what's called prior appropriations, first in time, first in right. In the eastern United States, it's a riparian law. If you're next to a river, you have a right to use it and not hurt your downstream neighbor. But in the West, it was first in time, first in right. And because of that, we have a situation where we have people with senior water rights that they've had for a century or so, and people with junior water rights. And during a drought, the senior water right holders may actually get all the water they want, and junior water right holders get cut off. There has been conversation about developing market mechanisms, for example, to let a senior water right holder market water to a junior water right holder. If they become more efficient, they can still grow what they want, but they've saved some water that they could then market, perhaps. There are conversations going on about modifying the water rights regime in California. It's intensely political. It's very difficult. It's technically difficult, it's legally difficult, it's culturally difficult. There are some experiments underway to let some kinds of marketing go on to try and address some of those issues, but that might be a long-term objective. I'm hoping there will be changes in the long run, but in the short run, we sort of have to work within the politics that we have.
Peter, Howard Bernstein, WUSA TV Washington. Excellent talk. I do want to talk something about California, because I read, I don't know, a month or so ago, that California, since the early 70s, has almost doubled the population, but it has done nothing as far as water storage capacity. And you're out there. Why? Why are the planners not planning?
Yeah, so that's a great question. It's not entirely true, although it's mostly true. The population has doubled enormously. By the late 70s, we had built out a massive water infrastructure in California, hundreds and hundreds of big dams, aqueduct systems to move water from the Central Valley to the southern part of the Central Valley for farmers and to the coast, the Colorado River aqueduct system, the Los Angeles aqueduct system. The infrastructure was largely in place by the late 70s. And we've added a little bit of surface storage capacity since that time, but you're mostly right, we haven't done much since then. Not because we don't want to, but because we built on all the good dam sites and some not so good dam sites, because we understand now the value of ecosystems and protecting a couple of remaining rivers that are not fully tapped. So we're moving away from a reliance on traditional storage to looking at this question of new sources of supply, like wastewater and desalination. We're building a big desalination plant in San Diego right now. There's been a lot of work on water use efficiency, and actually demand per capita has gone down to meet the needs of a growing population within a constrained water supply. We're not going to move water from the Mississippi. It's too far, too expensive. Rocky Mountains are in the way, big economic cost. We're not going to move water down from Canada for economic reasons and political reasons. This issue of peak water, that we're running into limits of our supply, mean if we're going to grow our population and our economy, we have to do things a little differently than we did in the 21st century.
It just seems to me that water is more important than a bullet train. We know there's going to be a lot of money spent on that. Are they spending enough? I mean, you're telling me stuff that obviously I don't know. I'm not in California. But are they spending enough to get that new supply?
Oh, so that's also a great question, and it gets to, well, first of all, we did just pass in November a $7 billion bond measure for a whole series of water investments. A lot of the money that's actually invested in water is not federal money or state money, it's local money. My water agency charges me for my water, and they take the money that I pay them, and they maintain the system. They upgrade it. They've spent, my particular water agency has spent $250 million in the last few years on earthquake strengthening of the system. There is investment going on. The type of investment is changing. Whether it's sufficient or not is debatable. Whether it's a question of state investment in water infrastructure or a bullet train is a difficult political decision. I would argue we need a bullet train, but we need smart investment. We need smart investment in our water system as well. That's a political conversation.
Great talk. Well, let's get back into California and these agricultural belts. That groundwater map that you showed,
yep.
That was a disaster. I mean, that's a disaster. I mean, how long before you get down to no water left? I mean, there's a line miles long. It's $1 million to drill a well.
Right.
You can't get much deeper. I mean, this is where we grow our food. I mean, just how dire is this?
It's a great question. This groundwater problem in California is partly the result of the drought and lack of surface water that makes farmers have to go to groundwater. It's partly a result of the fact that California, among all the 50 states, up until last year, had no groundwater regulation and law. It was a free-for-all. It was the classic tragedy of the commons. If you had $1 million and could drill a well, and some of the big corporate farms are doing that, you drill deeper, and you pump that same common aquifer, and the guy who has the shallower well suffers and goes dry. That's the tragedy of the commons. In part because of the drought, and in part because of the disaster in the southern part of the San Joaquin, the politics sort of aligned last year, and we did pass groundwater law that's going to require monitoring groundwater, reporting groundwater, and what we call adjudicating or coming to an agreement about how a groundwater basin is ultimately going to be allocated and used. It's going to take years, but those groundwater basins that are overdrafted will ultimately have to come back to what we call sustainable yield, where the amount of water that goes in and the amount of water goes out are equal, so that the groundwater levels stabilize. In drought years, we'll still pull out more than goes in, but the idea is that in wet years, you let it recharge, which we're not doing now. And if ultimately recharge equals outflow, we don't have that problem, and we allocate among the different users. We decide who gets to use it. Maybe there's an economic strategy that lets there be some balancing. But until we get that part of the puzzle into alignment, we're not going to have a sustainable system.
Joe Berga from WTAJ-TV. You mentioned a new desalinization plant that's going up. Are they making progress, and are we robbing Peter to pay Paul? Is it putting a pretty good carbon footprint to do this?
Great question. So here's the story on desalination. We know how to take salt out of water. It takes energy. Either you boil the water and the fresh water goes off and the salty water is left behind, and there's big, massive industrial systems that use that process, or you use what are called membrane systems, reverse osmosis, other kinds of membrane systems, where you have membranes that separate out salt ions from fresh water, and those are big technology systems being built as well. Places that have very little water and a lot of money have for years built desalination plants. You think about the Persian Gulf and the Arabian Gulf, Saudi Arabia, the United Arab Emirates, Kuwait. Those are places that don't have local water supplies. There are no rivers, there's not much rain. They've been dependent on desalination for a long time, and they have the money to pay for it. A place like California has not had much in the way of desalination for a long time because it's very, very expensive, largely because of the capital infrastructure and the energy cost. The costs have come down over the last few decades. It's become cheaper. The desalination plant that San Diego is building at a place called Carlsbad is still going to be the most expensive new water in California. It's still more expensive than conservation and efficiency. I can save a lot more water cheaper by paying people to put in low-flow toilets and efficient washing machines and get that same amount of water than that desal plant in San Diego was going to provide. But they decided to build it. It's drought proof. Doesn't matter what happens to the weather. That desal plant can keep producing water. It's politically independent. They're not going to be dependent on Northern California or Los Angeles for water, and San Diego is very sensitive to that. So they decided to build that plant. It'll be the first, as I said, it'll be the first big municipal desal plant in California. It'll still only provide 5% of San Diego's supply, so it's just sort of one piece of the puzzle. And I think we just have to be smart about the kinds of things we choose to do over time. But I do think there will be more and more of desal in our mix.
Peter, sort of on that same theme, once rain falls or snow falls from the sky, the lawyers get involved. And there's some very good examples of really bad water decisions that were made when the lawyers got involved. And then some where good things happen when the lawyers got involved. What's your, I mean, so, you know, this is physics and it's also society and it's policy and it's all this other stuff. Where do you see the biggest problems? I mean,
With lawyers?
That was my sense. Okay. But I mean, can you elaborate on that? I mean, you know, part of our inability to solve these problems has to do with the way that we handle these things, and the lawyers get involved, et cetera. So.
Well, I'm no fan of water lawyers, but the truth is, and this comes back to the question that was asked earlier about water rights, we've built in the Western U.S. and globally in different places, different kinds of water institutions and infrastructures. We've put in place laws that allocate water among different users. It's not just technology, it's institutions. And I'm sorry to say that there's not going to be any shortage of demand for water lawyers, not just water, but water lawyers over time in the Western U.S., because that's a part of the system we've put in place. And we just have to manage it. So, but could I actually come back to Joe's question? I forgot to answer one part of it. Because of the energy cost of desalination, there is a greenhouse gas footprint. It's one of the most energy intensive forms of water that we have. But whether or not we emit greenhouse gases when we desalinate depends on the energy system we have. Perth, Australia built a very big desalination plant in Western Australia during a bad drought. And they built 80 megawatts of wind turbines at the same time to feed into the grid to help offset greenhouse gas emissions. So whether or not we build desalination and whether or not there's a big impact on emissions, that's this energy-water nexus I hinted at in my talk, partly depends on our energy choices. And that's an important factor that we ought to consider.
You know, the one thing that, I hope I don't offend, the one thing that bothers me about that is put the wind turbines, I mean, to counteract it is one thing, but it's still one big power grid.
Yeah.
And so those could have been built already to help out in the first place. And, yeah.
No, that's absolutely right. And that, you know, that's an energy policy question about how we want our energy system to look in the future. Australia built it because at the time when they were debating the desal plant, this question about greenhouse gas emissions came up, and they were still are largely a fossil energy system. But in order to eliminate or reduce public opposition to the desalination plant, they decided they would address directly the greenhouse gas implications of adding that much energy demand to the system.
Peter, James Baylog, Earth Vision Institute. I tend to think of these aquifers as confined stratigraphic layers, you know, like a rock layer in the ground. So when you talk about the southern part of the San Joaquin being drawn down 50 or 60 feet, how thick, in fact, is that layer of water, or do I misunderstand the basic nature of that? In other words, how many years can you keep on having that kind of drawdown before you hit the bottom and you're in dry rock?
Yeah, so every groundwater aquifer is different. It's based on the geology, it's based on the refill, it's based on the soil conditions, and so on. The problem with, you could draw down aquifers completely, but really the problem is you draw down aquifers and the levels drop, you run into an economic problem long before you literally run out of water. There's a lot of water in groundwater aquifers to very deep layers in California or the Ogallala and the Great Plains under Texas, Oklahoma, Nebraska, Kansas, and so on. The problem is economics. The problem is as those levels drop, it becomes more expensive to pump because the cost of pumping is literally related to the amount of water you pump and the height you have to raise that water. And in the Great Plains, in the Ogallala, farmers have already gone out of production or back to rain-fed agriculture only because they can no longer afford the water cost of pumping from the decreased height of the aquifer. And we're beginning to see that in California. If you have $1 million, you can drill a deeper well and you can pump if you're feeding high-valued crops. But if you have a well that's not that deep, then you run out of water because your well isn't deep enough.
Dale, like the Weather Channel, and I think another complication there is, and I think the Weather Channel, we actually went out there and did a story with the amount when you empty or really deplete the water in some of these aquifers, the land is settling. Yeah. And therefore, those aquifers now no longer have the capacity, even if you got the rain, to hold the amount of water they once did.
Yes, that's a great point. I should have mentioned in response to James' question, under some geological conditions, when you pump groundwater out, I'm just repeating what you said, the land actually settles, and it makes it difficult to recharge those aquifers. There are some groundwater aquifers, however, where the land doesn't settle and where recharge is possible. And this gets back to this question that Howard asked earlier about infrastructure and storage. We're increasingly thinking not about surface storage. We can't find places to build reasonable dams anymore, but groundwater storage. We have these overdrafted groundwater aquifers. If we can store water in wet years in groundwater, you don't lose water to evaporation, you don't have to build a big infrastructure, a dam, and use that water in dry years. That's a storage option that California is increasingly exploring. And there are institutional questions about making sure that you put the water in and you know who's taking it out. Gets back to this earlier question about water rights. But that's a new option for California and much of the rest of the world, frankly.
Peter, Dave Jones. Again, the conversation has taken us a little bit over time, but it's very dynamic and intriguing. So thank you very much. I actually have two questions. Hopefully they'll be short answers. Number one, sitting before you are broadcast television meteorologists who have a great desire for visuals and the ability to take a look at water resources and perhaps put them on the air if those visuals were available. And I've desired for years to have a visualization of aquifer levels. So you can have a bowl and say, this is right below Atlanta, this is how much we have. Is there any advancements, are there any advancements being made to make how much water we have in the aquifers visual so that can be communicated on the news? That's my first question. The second one is shorter. Have you used any NASA satellite data or information to put to work to help you tell this story of the, Jim showed some great satellite data and things like that, but are you moving in that direction, or what else do you need to help tell a better story about the diminishing water resources?
Yeah, those are great questions, and I'll try and answer them both together. The one thing, and having sat through some unbelievable graphics over the last couple of days, there's nothing I can teach anybody in this room about graphics. The GRACE satellite is probably the best example. The GRACE satellite is a set of twin satellites that measure gravity fluctuations. They travel around the planet. They measure changes in gravity. It turns out, as you heard from a previous speaker, one of the things they're really measuring is changes in water. Water's pretty heavy. And when you lose water during drought from soil moisture, or you overpump groundwater aquifers, or you see a heavy monsoon season dumping a lot of water in a particular region, you see changes in those. You see very graphically with the GRACE graphics changes in water availability in groundwater. I've used a lot of the GRACE graphics. They're very enticing. They're very influential, I think, in helping us understand the movement of water from one place to another and the extraction of groundwater from particular parts of California, the Central Plains of the U.S., India, China. You can really see water management problems pretty visually.
Awesome. Well, Peter, thank you very much. This has been a great session. Terrific.